Hi, welcome back. This is now section 7.1 in Math 1620, and we want to take a look at finding the area between curves. So the theory is fairly simple. You may have to remind yourself of how the Riemann sums worked. So to get the area underneath a curve, so if we have some curve in the plane, and we want to know the area underneath that curve, we can approximate that area with a bunch of little rectangles. And then, of course, we could then take the limit as the number of rectangles goes to infinity. And at the end of the day, we get the area underneath that curve. Okay. So the building of that integral thing that we work with then is first identify some kind of abstract rectangle in there located at some position x sub I with a base change in x. And then the curve, if it's designated by the function f of x, the curve height tells you the height of the rectangle. So we could take that one particular rectangle I have there in the middle, put some purple on it, this guy right here. We could look at that guy individually and give it an area, designate the area of it. So we could say, well, this height here is f of x sub I. And then the width of the base change in x. So it's just base times height. And to get the approximation of the area, what we did was sum all of those things up, going from I equals 1 to n of this f of x sub I, change in x. And then we took the limit of this thing as the number of rectangles went to infinity. Right? And that gave us the integral that we all know and love, f of x dx from a to b. Okay. So now in our new setting, the idea what we're trying to do is find the area between two curves. So let's say I have maybe this curve here, call it f of x, and then maybe a simpler curve below it, call it g of x. And I want to integrate from a to b to find the area between these two curves. Okay. We can go through and do the same process all over, just filling up this region with a bunch of little rectangles. There's our generic rectangle in the middle. And then we can, again, try to find the area. Let's say this is our generic rectangle. We're always going to position it at some point x sub I in that interval from a to b. The base, we'll say, is change in x. Okay. So from, so the base is change in x. And then what's different this time is the height, right? That's going to be a difference. But anyways, we could say the area of that is just the height of it, which is a difference between the distance from the x-axis to f of x, which would be like this distance, minus the distance from the x-axis to g of x, which would be this smaller distance. Okay. So in that case, the height is f of x sub I minus g of x sub I, and then times change in x. And again, we could sum all of those up to get an approximation. And take the limit as the number of rectangles goes to infinity. But at the end of the day, what you end up with is just the difference between these two functions, f of x and g of x. Okay. In general, I think of it as top curve minus bottom curve, but that doesn't always work because we have those different orientations. So if it is oriented in what they call the vertical rectangle direction, it is definitely going to be top curve minus bottom curve. Okay, so in this case, let's say the top curve is f of x. and the bottom curve is g of x. And if we want to know the area between those curves from A to B, it's just going to be presuming that maybe you're thinking of a guy who's walking across, or a gal walking across, or anyone walking across, collecting up these rectangle areas. The top part is going to be the f of x, the bottom part will be the g of x. So we have f of x minus g of x dx from A to B. Okay. The other orientation is where everything's in terms of y, and in that orientation, you're collecting rectangles as though you were walking up, I always call it walking up the flagpole. Okay, so here's my little individual, and there's this bag of rectangles, and he's collecting, or they are collecting the rectangles going from maybe some position C to some position D. And the orientation of the rectangle, let's say, is horizontal. Okay. Let's call, and in this orientation, it's like the top curve is the right curve, and the bottom curve is actually the left curve. So it's a little weird, but I'll call the top guy h of y, and then the bottom guy g of y. And so our integral in that case is going to look like, and I hit the button again, sorry. For different notepads, it's different buttons, but all right, enough about me. Integral from, whoops, that's supposed to be C to D now. And now again, the top curve is the right curve, and the bottom curve is the left curve. Okay, but the idea is the same. It's basically you're just adding up a bunch of rectangles and then taking the limit to produce this integral. Okay? So you can often think, some people think of the integral symbol as kind of like the summation symbol, just stretched out vertically. Okay? All right, so those are our two forms. Let's get into kind of what the book has for us, or the homework, in other words. The first problems are just kind of fill in the blanks. You don't have to do any work, and they've even given you the pictures. For example, number 1, the integral from 0 to 2. Whoops, they don't even give you that, right? They just want you to fill in the blanks. So they give you two curves, and then they want you to find the area between the curves. So like on my test, I would expect you to sketch a graph of those. And if, you'll have your calculator there if you really don't know how to do this, but you should kind of have an idea of how to graph these by hand. For the first guy, y1 equals x squared minus 2x, you can find the intercepts by setting it equal to 0. So I have an intercept there and an intercept here. And then to get the vertex, the x-coordinate of the vertex is negative b all over 2a. So it'd be negative, negative 2 all over 2 times 1, where a and b and c come from the original quadratic. The form's always x squared plus bx plus c. Okay. So this is going to be positive 2 over 2, which is just 1. And then to get the y-coordinate, you put it back into the original function for x, and you'll have 1 minus 2, which is negative 1. Okay, so there's our parabola. Then the curve y equals 2. That's just y is always equal to 2, and x is allowed to vary over the real numbers. So that's just going to be the x-axis. Right. So the region that's being enclosed by these two curves right here, that's the region we want to find the area for. Okay. So in terms of kind of collecting rectangles then, or accumulating area, let me draw my Riemann person. We're going to be running across the x-axis, picking up these rectangles that are oriented as I drew there in purple. So the top curve is the blue curve and the bottom curve is the parabola. Okay, so my integral, I'm going to be collecting rectangles starting at 0 and then going to 1, or is it 2? Yeah, it's 2, sorry. And the top curve is 0, and then I just subtract away the bottom curve, which is x squared minus 2x. And for this problem, that's all you got to do, and just substitute it in. You don't even have to simplify. Okay. That's the same for number 2. Number 3, they kind of give you the expression first, and then if you're having trouble graphing that, I probably would have a little bit of trouble graphing it. You could go the Desmos and get an idea of the picture. Of course, on the test, you won't have Desmos, right? So you want to be a little bit cautious as to how much you rely on your calculator. Okay? But anyways, one of the functions you could see in the integrand there, y equals x cubed all over 3 minus x. And then the other function, y equals x over 3, is just a straight line with slope up 1 over 3. And you could see the form of it. We want to find from 2 to 3. So if you look at the limits on the integral, you see the little red 2 and then the red 3 up on the top. That's where you're integrating. That's where you're collecting your rectangles going from 2 to 3. So it's maybe not even clear as to where those are. I can tell on the kind of the graph, it's going to be from this point over to here somewhere. So it's not going to be A, it's actually B. But you've got to be kind of careful because it's kind of hard to tell, right, on the graph. Is that at 2 or maybe a little less than 2? If I keep zooming in, is it going to change? Okay. You have to be super careful and with what's going on. The only way to really get at it, if you're not a calculator of some sort, you have to kind of find the intersection point of the curves. So just graphing the things, with a calculator may not be enough to figure out where to begin and where to end as you determine the regions. Do they need you to? No. But anyways, yeah, from Desmos, the curve is one of these goofy kind of things. The cubic looks like that. And then on top of that, you have this straight line going like that. And the question is, kind of where is 2 in this picture on the x-axis? And you could figure out where they literally intersect and see if that's where it's going to start adding up. Is that where the rectangles need to be added? How do I do that? Well, you just set the 2 functions equal to each other. And I multiply both sides by 3 to make my life a little easier because I just hate fractions. And yeah, you can see definitely algebraically speaking, you have that intersection point here at exactly 2. So the running person is going to be collecting rectangles starting at 2 and then going all the way over to 3, wherever the heck that would be. So maybe 3 is right here. I'd have to keep drawing my graph a little bit. So it's really this region here that they're after. And you can see that plainly, hopefully, in choice B here. And again, they don't really need you to evaluate it, but this is the same spiel, number 4, just determine which region. Number 5 was kind of annoying. I think I tried to do that in my lecture. I don't know if I have time to do it in my lecture. Everything's a bit long. I could do it here, and then, you know, if I don't get to it in my lecture, at least it'll be here. You can fast forward through it if you don't need to watch this. You can fast forward, and then when you're doing your homework. So some people like to watch my video and do the homework at the same time, you know, and pause the video. I don't know how fast that really is, though, because you are under time constraints. Okay, but anyways, here's our two curves. The parabola, you know, I kind of know what that looks like. The y equals 20 minus x. I'm just going to cheat a little bit and label the y-intercept, and then it goes down 1 over 1, so the slope is going to be something downwards facing. And then the x-intercept has to be at 20 as well. But, you know, you're going to have this parabola-shaped thing going up like this, and the region we want to kind of find is this region right here. Okay? So they want you to do it in two ways. The problem is two different methods. They want you to do kind of what they call the vertical oriented rectangles like this, and then horizontal oriented. The vertical oriented is the easy one. That's part A. Let's go ahead and try that real quick. So in that orientation, and of course we also will need the intersection points to tell our little guy or person where you're integrating, going from where to where, you know. So you got x squared equals 20 minus x. You got x squared plus x minus 20 is 0. So x plus 5, yeah, and then x minus 4 is 0. So x is negative 5, and then x is 4. So I'm going to be running from negative 5 to 4, collecting those little rectangles. The top of the rectangle is given by 20 minus x, and then you're subtracting away the bottom portion, which is given by x squared, okay, dx. And then it's just, you know, integrate, power rule, and the kind of annoying part is evaluating. Sometimes lately I've just been getting annoyed and I just go to my calculator and kind of figure it out, but it's up to you. If you show work, at least I could give you partial credit. If you don't show me any work, you know, you're on your own, so to speak. So what is this, negative 100 minus 25 halves. This will be plus 125 thirds. So it's kind of a bit of a nuisance. But what is this going to be? 80 minus 8 plus 100 is 172. And then minus 189 thirds plus 25 halves. And then find a common denominator and add it all up. 2 minus 378. I'm not doing this in my head. I already have it written out, in case you're wondering. Oh, you must be really good at doing mental math. No. No. 729 over 6. 243 over 2. Okay, so a lot of arithmetic there at the end, but like I said, if you have a calculator, I don't want to see decimals. Is kind of what I don't really want to see that. Hopefully you have a mode in your calculator that will allow you to kind of compute it without a decimal. If you got to use a decimal, you know, that's what you got to do. But okay, so that's the perfect answer. So with decimals, sometimes you have to approximate. An approximation, you know, at least for math people or my kind of math person, I see approximations as being bad because they're not perfect, right? In mathematics, the world is perfect. So anyways. So that's part A. Part B is a little nastier because of the orientation. The top and the bottom curves change as you move sort of up the flagpole collecting your rectangles. Okay, so here's kind of the picture again. And let me draw my little person running up the flagpole with his bag, collecting little rectangles along his way. and here's a rectangle here. Okay, but there's this frontier line right here, and at that line, the rectangle types are going to change. So see, in the first region, the top of the rectangle is given by this purple portion. And the bottom of the rectangle is given by this blue portion. But when you cross that frontier, then the top of the rectangle is given by the straight line. And the bottom of the rectangle is given by the blue curve. Okay? So we need also to put everything in terms of y. So our functions as they sit, y equals x squared, and then y equals 20 minus x. So in terms of y, you got to be a little careful, because if you take the square root on both sides, you're going to get a plus or minus. And that's why you now have 3 functions as opposed to just 1. On the other guy, it's x equals 20 minus y. So the purple curve here is x equals positive square root y. And the blue curve on the other side is actually x equals negative square root y. And then, of course, the black curve in terms of y is going to be 20 minus y. Okay? So you have to do 2 integrals. And that's what is that's the nightmare of it all. Right? So you have to do 1 integral from 0 to this point. And to find that point, you can substitute. You can set the 2 equations equal to each other and just solve. All right? So you can say, all right, square root of y is equal to 20 minus y. This is already looking kind of nasty, though. Squaring both sides, y will equal 400 minus 40y plus y squared. And then we have y squared minus 41y minus 400, and then equals 0. Yeah, that looks nasty. Let's see if I can go in a different direction. Set the x squared equal to 20 minus x. That will give us the x coordinate, and then we could just substitute the x coordinate into one of the y equations. Okay? So as an ordered pair, we're going to be first looking for the x coordinate. Oops, sorry. So there's 2 that we want to get our hands on. We need the y coordinates for each of them. But anyways, x squared plus x equals 20 or minus 20. So that's a lot easier to solve, right? So this would be x minus, or rather x plus 5, x minus 4. So x is going to be negative 5, and then x is 4. And then we could substitute those values to get the y coordinates, right? So negative 5, and then substituting it into this guy, the y coordinate is 25. So I'm going from, and then the other coordinate, sorry, is 4, 16. Right? So the running guy, the guy going up the flagpole here, the person is going to start at 0 and then go to this frontier place at 16. So I'm going from 0 to 16. And in that region, the top curve is the purple curve, and the bottom curve is the blue curve. Okay. And then we're going to change things, right? From 16 to 25, the top curve is the equation of the line, and then the bottom curve is the blue curve again. Gotta be careful with the signs. Okay. So, negative is plus, so you're going to have 2 square root y. I'll just factor out the 2. And you could think of the square root y as y to the 1/2. So let's just get it prepped for integration. Plus the integral of 20 minus y plus square root of y again. And then we'll have 2 times y to the 1/2 plus 2 halves is 3 halves, divided by 3 halves, same as multiplying by 2/3. Evaluate, plus 20y minus y squared over 2 plus y to the 3 halves times 2/3. Evaluate, and then, sorry, I just realized I needed something. And then, let's see what we got. Oh, so I have to evaluate from 0 to 16. So I have 4/3 and 16 to the 3 halves. That's just 4 cubed, which is 64. And then minus 0, and then plus, now I have to put in 25 and 16, right? So 20 times 25 minus, oh boy, 25 squared over 2 plus 2/3. 25 to the 3 halves is 125. And then I need to subtract away. 20 times 16 minus 16 squared over 2 plus 2/3. 16 to the 3 halves is 64, I believe. And I'm just going to go to my calculator at this point and see if I get it. Okay. So, do I have the right mode? Yeah. So 4/3 times 64 plus 20 times 25 minus 25 squared over 2 is 2/3 times 125 minus 20 times 16 plus 16. I'm distributing the negative, minus 2/3 times 64. Drum roll, and it's 2, yeah, I got it. So it's 243 over 2. So one of the problems with integration is later on, eventually, they'll get more complicated, of course, but you'll have more than one approach, and you'll need to be kind of flexible as to your approach, which way is the easiest. You kind of saw me struggling with that algebraically when I was determining the intersection points for my limits on my integrals. You have to kind of be flexible and be able to move back and forth between different methods to find the easiest kind of path. Okay. Okie dokie. Let's look at maybe number 7. Okay, so some of these you're going to have to graph the thing, which is kind of annoying. So let me hook you up with, let's see, the process in number 7 here. So there's some mild annoyances that we have to deal with. It's not going to let me try it again. I can't try a similar problem. Okay. All right, so you got to graph this thing using their little tools. They have a parabola tool, the 4th button down, and they have a line tool, the 2nd button down. So we need to use those 2 tools to pull this off. For the parabola, you need 2 points to plot the thing. And usually I go after the vertex. So I believe you always kind of have to start with the vertex. And then, so step 1 in the software, plot the vertex. And then just get some other point, maybe an x-intercept or a y-intercept. Okay, but for the vertex, the formula is always, the x-coordinate is negative b over 2a. So negative 4 all over 2 times negative 1. So that's 4 over 2, which is 2. And then you sub it back in. So negative 4 plus 8 plus 3 equals 7, I believe. So you know your vertex is going to be 2, 7. And then just get another point. So some other point. We'll go for the y-intercept. So if you plug in 0, you get out 3. So I have 0, 3. If you went for the x-intercepts in this, you might have a little bit of trouble, right? Because it's going to be nasty. It doesn't have a nice integer intercept. But 2, 7, where the heck is that? So I'm going to click on my parabola button, 2, go up to 7, click there, and then I need one more point, so 0, 3, I decided, and then click off of it to make it go black, like that. Okay. All right, so for the second function, g of x, that's x plus 3, you know, the slope is 1, the y-intercept is 3. So you have to click on the double-headed arrow. Some people always try to go over here to this thing. That won't work. That'll give you a line segment. Okay, that will not work. You have to click on the double-headed arrow button. I'll start at the y-intercept, which is 3, and then I'm going to use a slope, down 1, over 1, to get to the next point. Click off of it to make it go black. And then to get the region, the appropriate region, go over here to this paint bucket, fill, click on that, and then fill in the area. And that should be your graph. Okay, so it's a little tricky, I know. Let's do the best you can. Okay, so anyways, for this problem then we need to find the area as well. So it kind of looks like this. I'm going to need these 2 intersection points. It's oriented with vertical rectangles, so my running person is over here. I like to call him the Riemann person. Okay. So you collect up your rectangles. I need to go figure out where the person is running from, right? Where the rectangles live. So I need to set these 2 equations equal to each other. Okay. So I'll have x squared. Moving that over there, and then minus 4x plus 1 is minus 3x. Oh, well, that was nice of them. So you can factor that. And you get x is 0 and 3. Those will be your limits on your integral. And of course, the top curve is the parabola. And the bottom curve is the equation of a line. Sorry, I got an extra set of parentheses I didn't need. Then it's just a matter of simplify first. Please don't just integrate right off the bat. Simplify it first. Okay? That'll make life a lot easier in the future. 4x minus 3x is plus 3x, and then the 3's will cancel. Yeah, negative x cubed over 3 power rule, 3x squared over 2 power rule, 0 to the 3, so negative 27 over 3 is negative 9, plus 27 over 2. I guess. Find a common denominator. And you're going to get 9 halves. Okay, the video quiz problem then is number 18 from the book. They want you to sketch the region bounded by the graphs and find the area. So it's a lot like this problem we just looked at. Okay, so the curves, y1 is negative x squared plus 3x plus 1. And then the second curve, y2, is negative x plus 1. Okay, so that's your video quiz for the section. Okay. All right. Let's see what else. Yeah, we got some weirdly oriented places in number 10. This one, I sort of make sure I don't forget to do any of the hard ones. I think I do that one in class. Number 14 is kind of a challenge problem. I might end up having to do that one here. Let's try the vertical oriented curve here, number 10. So I have my functions, f of y is y squared plus 2, g of y equals 0, y equals negative 1, and then y equals 2. Okay. So first you want to sketch the graph, and for this graph here, it's just a sideways facing parabola. So y squared just looks like this. Okay? And if you add 2 to it, it shifts it 2 places to the right. So that curve will be like this. And then g of y equaling 0 is basically just x equals 0. So that's your y-axis right here. And then y equals -1 is a horizontal line right here. And y equals 2 is another horizontal line right here. So the region we want is this region. And our Riemann person is going to be going in this direction of the flagpole. Okay, so I'm going to be integrating from -1 to 2. And my top curve is y squared plus 2. My bottom curve is just 0. So this one should be fairly painless. So I got y squared plus 2 dy. So that'll be y cubed all over 3 plus 2y. Evaluate from -1 to 2. So 8/3 plus 4 minus -1/3 minus 2. And that'll be 8/3 plus 1/3 is 9/3, which is 3. And then 4 plus 2 is 6. So that'll be equal to 9. Okay, this one is kind of a little bit more tricky. We could do some shortcuts in number 11 to get the job done. So if it's not clear how to approach that, that's kind of what you're going to need to do. So if you wish, you can get a picture of it using Desmos. So it says, if it says use a graphing utility, then just go ahead and do it. Don't try to be a hero. Where's Desmos at? There you are. So we have y equals x to the 4th. I mean, you're still going to have to kind of figure out the intersection points to do your integral, the limits on your integral, and the regions where your running man is running. But, you know, get an idea here first. Equals x squared plus 4. Okay, so we got kind of a picture going. And over here in my note universe, number 11, it looked like that thing was kind of going down and then bouncing off the x-axis and then going back up. Okay, the two curves, f of x equals x to the 4th minus 4x squared, and then g of x is x squared minus 4. So x squared minus 4 is a parabola shifted 4 places downwards, and kind of just remembering what it looked like, it went down like this and then intersected and then probably hits somewhere down here and then comes back up like this. Okay, so the region enclosed by those two curves is going to be this junk, and this junk. So that would be this picture on the right here in this box. In order to integrate it, you kind of need 3 integrals if you're going to go from, you know, this is the Riemann person is doing vertically oriented rectangles, and I need to go from here to here and then a different integral because the curve on top and the curve on bottom change places. So you would need like 3 different integrals. To figure out the bounds then, are the limits on those integrals, you need to really find the intersection points. So I got to set them equal to each other. It's a quadratic form, which is nice. And then x is going to be plus or minus 2, and then plus or minus 1. Okay, so, I mean, brute force, you can integrate from -2 to -1, and the top curve in there is the parabola. Let me just put g if you don't mind, g of x, and then the bottom curve is the quartic, I believe. And then you need another integral going from -1 to 1, and the top curve in that little region is then the quartic. And then you need another integral from 1 to 2. where in that region the top integral is the quadratic. Okay, but that's too much work, right? Brute force, sometimes you got to do it, but it's better to kind of look for workarounds. And the workaround here is from the fact that both functions are symmetric about the y-axis. You could prove that, but just from a picture, I think we can shoot from the hip and say that it is symmetric. So what I'm going to do is figure out these areas and just multiply those areas by 2, right? Okay, so here I go. I'm going to integrate from 0 to 1, and in that region, the top curve is the quartic, and the bottom curve is the quadratic. And then I'm going to integrate from 1 to 2, and then in that region, the top curve is the quadratic, and the bottom curve is the quartic. I sure hope I'm saying that right. Pretty sure it's quartic. Okay. Clean her up. So I got x to the 4th minus 5x squared plus 4 dx plus the integral of 5x squared minus 4 minus x to the 4th. It's basically the same thing but with different signs. Integrate. So just doing power rules. And then evaluate. So first substitute 1 into the antiderivative, and then minus substitute in 0. Of course, 0, when I substitute it in that first antiderivative, will just be 0 minus 0 plus 0, which is 0. And then plug in 2 into the second antiderivative. And then I have to subtract away 1 plugged into that. And then again, I'm just going to go to my calculator, and hopefully it's set up in the right mode. Oops. And I'm getting 4. I want to be a little careful though, because I have to multiply it by 2, right? So what I found was just the blue area. I need to still multiply it by 2, so 2 times 4 will give me the official area, which is 8. Okay, good stuff. Let's see what else we got. Oh, the challenge question, the last question in there, is a little difficult. Not really, but maybe I should just leave it to you. Yeah, we'll just leave it to you. Number 14 is definitely a challenge. See if you can get it. If you can't get it, just send me an email. And I'd be more than happy to post it in Blackboard. But you know, try your best to get it, and hopefully you can. There's a trig one. I'll hopefully do that in class. Okay. So thank you for watching as usual, and I will see you next time.